An important question in chemistry is whether or not a particular reaction or process is spontaneous. Now, a spontaneous reaction or process is one that occurs on its own without continual outside assistance. You might want to note here that even spontaneous reactions often need an initial input of energy to get started. Recall the term activation energy from a previous module. The subject of chemical thermodynamics allows us to evaluate whether or not a reaction or process is spontaneous, and just as importantly, also helps us predict how far towards completion a reaction will be when it reaches equilibrium. On the other hand, the subject of chemical kinetics that we covered previously allows us to evaluate how long it will take for a reaction to reach equilibrium. A spontaneous reaction is not necessarily a fast reaction. Thus, the differentiation between kinetics and thermodynamics is important. Now, below is a diagram showing the energy changes involved in the rapid and very exothermic reaction of hydrogen and oxygen to form water, one that we put a link to a video on in a previous lecture. And this can help us distinguish between reaction kinetics and thermodynamics. So we have energy on the y-axis, reaction progress, meaning going from left to right is reactants to products. On the x-axis, the reactants at the higher internal energy, hydrogen and oxygen, the products at the lower internal energy, 2 molecules of water. Now recall from the kinetics chapter that in order for reactants to get to products, the system needs to go over this activation barrier. And this is the domain of chemical kinetics. This is what determines how fast hydrogen and oxygen can become water. The rate of the reaction depends on the height of the activation barrier, the size of the activation energy, and the temperature. And this was covered previously in the module on chemical kinetics. When the reaction occurs, of course, you know that the system releases internal energy to the surroundings. The change in internal energy is thus negative. The energy difference between the reactant and product states and whether energy was gained or lost by the system is the domain of chemical thermodynamics. And that's what this module is spending time on. Now, in first semester chemistry, you learned about the change in enthalpy for a reaction. Now, in real terms, we covered that as a review of General Chemistry 1 in the first 2 lectures of this module. However, to predict whether or not a reaction is spontaneous and to what extent the reaction proceeds, we will need to introduce a couple of things in this module. The first is the change in entropy, and subsequently, the change in free energy. Both of these terms you've seen before, and we'll mention that again, but we're going to introduce them at a little more fundamental level in this module. Now you might ask, why does predicting reaction spontaneity need to get complicated? Aren't reactions where heat is released, an exothermic reaction, delta H negative, wouldn't they be spontaneous, like the hydrogen and oxygen going to water reaction? That's highly exothermic, and it looks spontaneous to all of us. So wouldn't there be just that simple connection? And reactions that require heat input from the surroundings, endothermic reactions, ones with a positive delta H, wouldn't they be non-spontaneous? Because in a sense, you're going up an energy hill there, at least with regards to heat transfer. Generally speaking, exothermic reactions where heat is released are spontaneous. So for example, our hydrogen and oxygen to water reaction is highly exothermic, and this reaction is explosively spontaneous. And endothermic reactions requiring heat input from the surroundings are generally non-spontaneous. Here's an interesting example. If you combine nitrogen and oxygen to form nitrogen dioxide, if you went and made this reaction occur, it would require a heat input of 67.68 kilojoules. In other words, it's an endothermic reaction. Now, it's actually fortunate that this reaction is not spontaneous at normal temperatures, or else, think about it, the atmosphere is made up of mostly nitrogen and oxygen. Our atmosphere would simply decompose into a poisonous gas spontaneously. So we're thankful that this reaction is not spontaneous. However, there are examples of reactions and processes that are endothermic but still spontaneous. Again, there are examples of reactions and processes that require heat input from the surroundings. In other words, they're endothermic, but they still are spontaneous. Once started, they go by themselves, or they just go by themselves. Here's an example of a process that you see all the time. How about a flask full of 1 mole of ice, solid water, melting to 1 mole of liquid water at room temperature? You know that's spontaneous because you see that occur, yet this does require heat input from the surroundings. It's an endothermic process. Delta H is positive, so there's an endothermic process that's spontaneous. Here's another example. This reaction would be a little bit difficult to relate to, but it's an example of N2O5 in the solid form decomposing into NO2 and oxygen. This reaction is highly endothermic. It requires a large amount of heat energy to be absorbed from the surroundings, yet this is spontaneous at room temperature despite having a very positive delta H. So as previously stated, we'll first introduce the concept of entropy change, and then subsequently free energy change, and this will allow us to more accurately predict reaction spontaneity and the progress a reaction makes towards completion before reaching equilibrium. We will start with entropy S and the change in entropy, delta S. As I mentioned previously, you might recall that in a previous module, we briefly introduced delta S and delta G when attempting to predict solubilities. As promised back there in that module, we will now discuss the origin of these energy changes in a more fundamental way. Let's look at some background information on entropy and the change in entropy. A proper introduction to the concept of entropy requires us to at least briefly cover some background materials that experts in the field of thermodynamics, chemists, physicists, and engineers would insist that we consider. Here's one of them. A spontaneous process occurs in one direction only. The reverse of any spontaneous process is always non-spontaneous. Here's a thought experiment, but you could see this being done in the lab with a little difficulty. Suppose we had two connected flasks. Here's flask A, flask B, connected by a tube of glass, but there's a stopcock here, and we have gas only in flask A and no gas in flask B. So B is an evacuated flask, 0 pressure. We have gas at 1 atmosphere of pressure in A. And let's suppose we open the stopcock. Well, I think you know what will happen. Gas will very quickly at first go from flask A to flask B, and if we leave the stopcock open, the gases mix evenly between the two flasks. So you'd have half an atmosphere of pressure in one flask, half in the other, and This is a spontaneous process. It occurs without outside assistance, except for the assistance of opening the stopcock. Now you might ask yourself, would the gas ever all return to flask A? So could we get this situation here with the stopcock open and all the gas go back in A? And you'd say, no, of course not. So we'd say that the reverse process is non-spontaneous. We might just add that if you think about it, in reality, the probability of all the molecules returning to flask A is not absolutely zero, but it's so absurdly small that it could be considered to be zero. Let's re-examine the distribution of identical gas molecules in connected flasks. And we'll make a couple of changes. First of all, we'll use fewer molecules, although in the previous slide, we never counted the molecules. We just assumed at the pressures indicated there were lots of them. Also, we will label individual molecules in order to track them. So here's a simple case one. Let's suppose we have one molecule, we'll call it X. X could be in the left flask, X could be in the right flask. And so what we say is this situation is described by two microstates. We say, what is a microstate? Well, each of the possible arrangements of molecules in each case is called a microstate. So we have two possible arrangements, two microstates. And then we ask, what would the probability be of having all the molecules being found in the left flask? Well, all the molecules in this case is just one molecule, and the probability of it being in the left flask would be 1 out of 2. So this seems rather straightforward. Let's consider the case where we have two molecules and we've labeled them differently here. How would we rearrange these two molecules? Well, they could both be on the left. X could be on the left, Y on the right. Y could be on the left and X on the right, or they could both be in the right flask. Well, here we have 4 microstates, 4 possible arrangements, and the probability of all the molecules being found in the left flask, you can see, is 1 out of the 4 possible cases, and we can get this by taking 1/2, which would be the probability up here, times 1/2, or in other words, 1/2 squared, or 1 out of 4. Let's try 3 molecules. Well, if we did our homework here, we'd find the possible arrangements look like this, and you can check this if you want. I think I've done it okay and gotten all the possible combinations, and you can count these up, and there's 8 possible arrangements, or 8 microstates. And the probability of all the molecules being found in the left flask is now 1 out of 8 possibilities. And you can get that by taking 1/2 times 1/2 times 1/2 equal to 1/2 cubed, or 1 out of 8. Now you notice here that the power that I'm raising 1/2 to corresponds with the number of molecules I'm trying to arrange. 1/2 to the first power is 1/2, 1 molecule. 1/2 to the second power, 2 molecules I'm arranging, 3 molecules I'm arranging. This little footnote came up here because you may want to ask why the molecules are never found in the tube connecting the two flasks. Well, that's a good question. What we're assuming here is that despite what the drawings look like, the tube connecting the two flasks is very short, or we could say the two flasks were just joined at the opening, and so it's not a consideration here. So back to our formula. For n molecules, the probability of all the molecules being in the left flask would be 1/2 to the n power, where n is the number of molecules. So suppose we have a mole of molecules. That wouldn't be unusual in the lab. The probability of having all of them in the one flask would be 1/2 to the 6 times 10 to the 23rd power. And I can tell you that that's essentially 0. So for 1 mole of gas molecules, probability dictates that movement away from an arrangement where all the molecules are in only one flask is definitely a spontaneous process. Let's examine the possible arrangements of 4 molecules in 2 flasks. Well, I've done that for you here without parsing through all the different combinations. There's 16 possible arrangements, or 16 microstates. Now what I'm going to do is I'm basically removing the labels on the molecules and just replacing them with dots. Well, what am I trying to point out here? There are many more disordered microstates. In fact, 14 if we define a disordered microstate as a microstate where the molecules are not all in one flask or the other. So there's 2 possibilities where things look very ordered. Other than that, there's 14 out of these 16 possible microstates show a more disordered arrangement. Physical and chemical processes tend to proceed toward more randomized or disordered arrangements. You could look at this and say the reason for that is that there's just a much higher probability of a disordered arrangement. In our diagram with the 4 molecules, 14 out of the 16 possible arrangements are the disordered ones. So there's a much higher probability of finding the molecules in a disordered state. Physical and chemical processes tend to proceed toward more randomized or disordered arrangements. An increase in disorder or randomness is associated with an increase in entropy, a positive delta S. Now we've emphasized randomized arrangements of matter. This is called positional probability. In reality, an increase in entropy, a positive delta S, is also associated with an increased dispersion of energy among the various molecular motions, translation, vibration, and rotation during a reaction. We'll have more to say about that soon. A spontaneous process, it turns out, is irreversible. Now we want to pause here and make sure we emphasize that this goes beyond stating that the reverse process of a spontaneous process would be highly unlikely. However, it does not mean that we can't push a spontaneous process backwards in the non-spontaneous direction, since we could always expend energy to do so. What it does say is that a spontaneous process cannot be reversed without producing a net change in either the system or the surroundings. Let's consider another thought experiment. We'll consider the isothermal expansion of an ideal gas. Well, what's an isothermal expansion? An isothermal expansion is an expansion at a constant temperature. And remember, an ideal gas is a gas whose pressure, volume, and temperature behavior are exactly predicted by the ideal gas law. Well, let's look at our thought experiment. Let's suppose we have 2 chambers. One side is a vacuum. It has no gas molecules in it. The other side contains gas molecules. And it's separated, these 2 compartments are separated by a movable partition, meaning we could just pull this out and remove it if we wanted to. But at the end of the vacuum side, there's a piston. Now let's remove the partition and you can predict what happens. Gas fills the entire space. No surprises here. While the partition is removed, the gas spontaneously fills the vacuum. So this process, after you remove the partition, is spontaneous. No work is done by the system during this expansion. Well, what do I mean by that? Well, the piston here never moved, and so there's no pressure volume work that's being done, and no heat is transferred into or out of the system meaning this gas in this box, because it was an isothermal expansion. Now let's try to return this box to the original state, where we had gas on one side and not on the other. Well, the only way we can do that is we'd have to move this piston, and we could push the gas back so that it's only in one half of this container. So the gas arrangement looks identical here, but something has changed. Returning to the original state, the gas in only half of the container, requires work by the surroundings on the system in moving the piston. So yes, we reversed a spontaneous process, but not without producing a net change in the surroundings. The surroundings lost energy in the form of work. So in our definition of reversibility, the spontaneous gas expansion that occurred after removal of the partition is irreversible. Now, experts in thermodynamics will tell you that there is one and only one reversible pathway back to the original state. In other words, there is one pathway to go from here back to the original state of the gases in the two halves of the chamber. That pathway would require an infinite number of infinitely small compressions of the piston and would take infinite time. But who has time for that? Therefore, any real process is irreversible. Again, what we mean is irreversible in the thermodynamic sense. We could always reverse it, but we can't do it without introducing a permanent change. Another thing we want to talk about entropy is that it's a state function. As is true for both internal energy E and enthalpy H, which is covered in first semester general chemistry, or in the first two lectures of this module, entropy S is a state function. This means its value is dependent only on the current state of the system, temperature, pressure, phase, composition, and not on how it arrived at that state. Now, functionally, this just means the following. We're interested in calculating the difference in entropy between a final state entropy and an initial state entropy. Again, the value of delta S relies only on the difference between the initial and final values of S, and not on the exact energy pathway taken to get from the initial state to the final state. In the 1800s, Boltzmann developed a mathematical relationship between the magnitude of S for a particular state of a system and the number of microstates associated with that state. Boltzmann's equation is the entropy S equals this constant K times a natural log of W, where W is the number of microstates and K has the value 1.38 times 10 to the minus 23rd joules per K. So this equation gives the entropy S of a certain state of a sample consisting of W microstates. The units of entropy S are thus joules per K, since the natural log of the number of microstates is unitless. So the entropy S of a particular state increases in proportion to the number of microstates that are required to describe that state. Now, how would we determine the sign of delta S? Let's do an example. Suppose you had a sample of 1 mole of gas at a certain temperature T1 in a certain volume V1. You then simply allow the gas to expand into a volume that's now twice as large, 2V1, but you keep the temperature the same at T1. We're going to use Boltzmann's equation to determine the sign of delta S. So the entropy of the initial state, that would be this 1 mole of gas at this temperature at volume V1, we're going to label S initial, and it would be K times the natural log of the number of microstates needed to describe this initial state. This would be 1 mole of gas occupying V1 at T1. The entropy of the final state, SF, would be Boltzmann's constant times the natural log of the number of microstates needed to describe the final state. Remember, the final state has twice the volume of the initial state, but the same temperature. We said delta S would be the final state entropy minus the initial. So we're going to take the final state entropy right here, K times ln of WF, and subtract the initial state entropy, K times ln of WI. If we factor out the K, we'd be left with K equals ln of WF minus ln of WI. And if you recall the rules of logarithms, this term here is the same as the ln of the ratio of WF over WI. So we have delta S equals K times ln of WF over WI. Now ln of WF over WI has to be greater than 0 since the number of microstates in the final state is greater than the number of microstates in the initial state. Well, why is that? Why is WF greater than WI? Because the final state of the gas exists in twice the volume that it did before. The increased occupation volume results in a greater number of arrangements or microstates for the gas in the final state. Therefore, delta S is greater than 0 when the volume expands, because there are that many more microstates for the gas to occupy, so randomness increases and delta S is greater than 0. Again, based on our previous discussion, this all makes sense. Delta S should be positive for a process where a gas expands into a larger volume, thus becoming more disordered, in other words, described by a greater number of microstates. Well, at this point, you might say, can we please get actual numbers in units for entropy and change in entropy? I think we did get some units for entropy. We haven't done very well in getting actual numbers. Well, experts in thermodynamics tell us that it is possible to measure delta S for an isothermal process, meaning get a real number, if we divide the net heat flow for the reversible pathway by the absolute temperature. So we'll say delta S is equal to the heat flow for the reversible pathway divided by the absolute temperature. You might ask, where are we going to find a set of conditions or a reaction or a process where this set of conditions will give us a change in entropy? Phase changes, as measured in a lab, are isothermal processes. They occur at a constant temperature, and we can certainly measure temperature in the lab. So how are we to measure the heat flow of the reversible pathway since no real processes are reversible? Well, for an isothermal phase change taking place at the appropriate transition temperature, in other words, for example, at 0 degrees C for the ice-water change, or 100 degrees C for the water-to-water vapor change, transfer of heat between the system and the surroundings is reversible since the two relevant phases are in equilibrium. Let's do an example. Let's calculate delta S, meaning get a real number, for the melting, remember that's also called fusion, of 50 grams of ice to water at 0 degrees C, 273 Kelvin, given that the heat of fusion of water is 6.01 kilojoules per mole. Well, let's calculate the change in entropy for this fusion process. It's going to be equal to the heat flow for the reversible pathway divided by the absolute temperature. We're going to say the heat flow for this reversible pathway, remember the system is at equilibrium, it's at 0 degrees C, is just the heat of fusion divided by the absolute temperature. 6.01 kilojoules per mole divided by 273 K is equal to 0.0220 kilojoules per mole per K. And we need to adjust for the mass of the sample and then convert kilojoules to joules. So we take our kilojoules per mole per K and we adjust for the fact that we don't have a mole, we have 50 grams. And then we're going to convert kilojoules to joules, and we get a result of 61.1 joules per K. So for the process of ice melting to water at a constant temperature of 0 degrees, the change in entropy, delta S, is positive. That makes sense because you're going from a ordered solid to a disordered water state. So we have an increase in entropy. Delta S is positive. How about if we think about the reverse process here? Let's say we want to calculate delta S instead of for the melting of ice to water. How about the freezing of 50 grams of water to ice at, again, 0 degrees C, 273 K, given that the heat of fusion of water is 6.01 kilojoules per mole. Well, heat energy would be released during the freezing process, so it would be equal in magnitude but opposite in sign to the delta H of fusion. So when we set up our example, it's the exact same calculation we did for the melting of ice to water, but now we're going for water to ice. So we're going to put a minus sign in front of the delta H of fusion. We reverse the sign. So we get exactly the same number for delta S, but opposite sign as we did for our previous example where we were looking at the melting of ice to water. If we adjust for our sample size, 50 grams, and convert to joules per K, we get minus 61.1 joules per K. So for the process of water going back to ice, the change in enthalpy delta S is negative. Again, that makes sense. What we're doing when we go from water to ice is we're decreasing the disorder. Makes perfect sense. The other way you can think about it is that you're increasing the order. In any event, delta S is negative. So let's summarize. A spontaneous reaction or process is one that occurs on its own without continual outside assistance. A spontaneous process occurs in one direction only. The reverse of any spontaneous process is always non-spontaneous. A spontaneous process is irreversible. As noted previously, keep in mind that this is irreversible only in the thermodynamic sense. It certainly is sometimes possible to force a reaction in the reverse direction, but not without making a net change to either the system or the surroundings. Entropy is a state function. Physical and chemical processes tend to proceed toward more randomized or disordered arrangements. An increase in disorder or randomness is associated with an increase in entropy, delta S, that's positive. A decrease in disorder, or in other words, more order, is associated with a decrease in entropy, delta S being negative. We've heavily emphasized the relationship between delta S and positional probabilities. For example, entropy increases when molecules are suddenly given a larger volume to occupy, or undergo phase changes from solid to liquid to gas, or just more molecules are added to the same volume. All of these changes provide an increase in possible arrangements or microstates and thus positive delta S values. As we mentioned briefly before, going forward, you need to keep in mind that entropy is also associated with energy dispersal. For example, we say entropy increases when the temperature of a gas sample increases due to greater energy dispersal from the higher kinetic energies and the broader distribution of molecular speeds. Greater molecular complexity, more in different kinds of bonds, leads to greater energy dispersal and higher entropy. For example, we can compare a couple of simple molecules. The absolute entropy of ethane, C2H6, which contains 6 CH bonds and 1 carbon-carbon single bond, is found to be about 200 joules per mole per K, while that of methane, which contains just 4 CH bonds, is found to be about 186 joules per mole per K. There is greater energy dispersal, a greater number of bond stretching and bending modes in ethane. Now, we will introduce more ways to calculate delta S values for chemical reactions and to predict reaction spontaneity in upcoming lectures.